Hi, everyone. Welcome for some of you to the physics department, a rare occasion, and I love it. Let's make it happen more often. So my name is Marcelo Gleiser, and I direct the Institute for Cross-Disciplinary Engagement here at Dartmouth. And one of the things that we try to do is to have a fellows program that attracts people who are interested in thinking about important questions in a cross-disciplinary way. It is from the scientific, humanistic, social sciences perspective. And we have Michela and Michael Sprevak, her husband, who is a cognitive scientist, visiting us for about 3 weeks now. And I'll introduce Michela in a second. I just wanted to let you know that April 22nd and 23rd, we're going to be having this amazing conference here on
The Blind Spot at the Search for Truth. You come up with the title.
Yeah, it's a hard way of, it's beyond what we mean about truth and reality in science, and it really covers many different aspects of it. It has Buddhist scholars, it has physicists, it has philosophers, cognitive scientists, and I'm going to advertise it more broadly in the next week, but I hope you're all going to come. It should be quite something. But today we have Michela Massimi here. She's a professor of philosophy of science in the Department of Philosophy at the University of Edinburgh. She's affiliated with the Higgs Center. It turns out that Peter Higgs, he is a professor at Edinburgh too. So there's the Higgs Center for Theoretical Physics and a fellow of the Royal Society of Edinburgh. She did her PhD at the London School of Economics. She was a junior research fellow at the Drude College at the University of Cambridge, and a visiting professor at the University of Pittsburgh in the fall of 2009, and at the Department of Philosophy at the University of Florence in the spring of 2016. She then moved for 3 years to the Department of Science and Technology Studies at the University College London. And
it's actually 6 years. I was there for 6 years.
Yeah, 6 years.
Yeah.
From 2005 to
2012.
2012. Mm-hmm. And then from then
to Edinburgh. Mm-hmm.
She has a very extensive CV, and physicists tend to be very stingy when they give introductions as opposed to humanists. So I compressed it a lot, okay? So her primary research interests are on philosophy of science, the history and philosophy of modern physics, and Kant's philosophy of nature. In 2015, she was elected vice president of the European Philosophy of Science Association. In 2016, she was elected corresponding member of the Académie Internationale de Philosophie des Sciences. She is the recipient of the Royal Society's Wilkins Burnham Redawar Medal and Lecture in 2017 for her interdisciplinary work and communication of philosophy of science, especially of modern physics. And from January 2016 until December 2020, she is the principal investigator on a 5-year European Research Council consolidated grant on Perspectival Realism, Science, Knowledge, and Truth from a Human Vantage Point. And today she's going to talk to us about the discovery of the electron and its impact at the time in Europe, and I'm not sure about the United States or not, and what it means to say that something exists or doesn't exist from a physics perspective.
Thank you so much, Marcel. That was a fantastic introduction, and the talk can only go downhill from this point onward. So thank you all for coming, and thank you for being here. Can you hear me okay in the back with the microphone? Okay. And thank you for bearing also with my Italian accent. I'll try to speak slowly. I gave a bit of a deceiving title, as Marcelo was pointing out. There's lots of ism in the title, realism, perspectivism, but this is really a talk on history and philosophy of modern physics, which is really one of the areas that I primarily work on. And it's part of this project founded by the European Research Council. That's why there is the European flag over there. That has been running from 2016 to 2020. Now, the project is a project in philosophy of science, and it addresses a very, in a way, simple question, the question of how can we be realist about science while taking also on board the idea that our scientific knowledge is perspectival. It's from a specific point of view, which means it's historically and culturally situated. Now, for those of you that may not be familiar with the idea of realism, roughly the idea is that to be a realist about science is to believe that science is in the business of telling us the truth about the world. So to call oneself a realist in science is to believe that to the best of our knowledge, our best scientific theories are going to be approximately true. Obviously, mistakes can be made and theories are revisable, but there is this intuition behind realism that the purpose of science is to tell us a true story about the world. Now, that intuition seems to prima facie be in tension with this other intuition that goes under the name of perspectivism. So the idea that our knowledge is situated is from a specific point of view, it's historically and culturally situated, because if that is so, how can we ever claim to be in a position of knowing that we have got things right, that we're approaching to the truth? The story I want to tell today is a story of success for science and a positive message. So it's a story of how we came to be realist about the electron, in particular about the electric charge, despite a plurality of ways of knowing, despite the plurality of perspectival representation of the electron. And so lots of books have been written by wonderful colleagues in the history of physics. You might be familiar with some of these books that really have delved into a very complex episode in the history of modern physics of how we came to discover the electron, how we came to have our realist beliefs about the existence of electrons. And what is interesting is that if you look at the history of 19th century physics, there was a variety of views, of images about what the electron really was. So these are just three of them. We start with George Stoney in England, who identified the electron as a minimal unit of electric charge. And then we go on to George Fitzgerald and Lorentz in Germany that didn't talk about the electron, but they talk about an ion. And their reasoning was very much entangled with the ether theories, very popular at the time. And then we get, obviously, the JJ Thomson, one of the main characters of the story I'm going to tell today, who in 1897, 98, working with cathode rays experiment, discovered what he called the corpuscle. I don't know whether you want to give the demonstration now, or do you want to give it later? So we're going to have, we have this privilege of being in a department of physics and astronomy. So we actually have the experiment, we have the instruments, the cathode rays, and Marcelo is going to give a little demonstration of some of the evidence that JJ Thomson had for the discovery of the electron that probably won't be very familiar to some of you. But
okay, so we have a cathode tube here that basically is an electron gun, and I'm going to activate it by creating an electric potential difference between two parts. And here, can you guys see the blue?
That's like a fluorescence, a green.
This is it. This is a gun flow of electrons. And what's really wonderful about this is that you can manipulate, if you have a magnetic field, or actually if you have an electric field, you can turn the beam in different ways. If you have a magnetic field, you can actually bend it. It will.
It's going all the way up, you see?
Basically, the magnetic field is being created by those Helmholtz coils around here. And you can actually make it go all the way around and loop it. It's very beautiful. This is a great one. It's a new toy. We just got it.
It's amazing. Because, I mean, JJ Thomson didn't have anything as fancy as this. I mean, he had cathode rays as a long tube, and he was able to manipulate, as you just said, cathode rays with the magnetic field, and was able to observe that depending on how you increase the magnetic field, this fluorescence can change direction, okay, can be bent by the magnetic field. But obviously the key question is, what's happening here, okay? What is this green light? And the explanation that we have today is that, well, cathode rays, the green light, is nothing but a stream of electrons. Electrons are negatively charged particles, so they interact with the magnetic field. and you can intervene and manipulate with them and change their trajectory. So that was the evidence that led JJ Thomson to his discovery of what he called the corpuscle at the time. Now, the interesting part of my story here is that JJ Thomson didn't call his object an electron. He called it a corpuscle. And even in his Nobel Prize speech, he called them carriers of negative electricity. He didn't call them electron. And that's because really at the time, the term electron was being used by people like Stoney to indicate something quite different from what Thomson had in mind about this corpuscle. So this particular episode in the history of physics raises interesting question for realism and perspectivism about science. And what I'm going to do in the next slide is just to introduce you 3 philosophical views that you find in philosophy of science, okay? And we're going to briefly explore some of them. So what kind of realist can one be about the electron or about any other entities you can think of in physics, okay? You can think about the Higgs boson, black holes, but also DNA, viruses, any kind of scientific entities in any kind of field. In decreasing order of strength, philosophers have been defending various positions. So the probably strongest view goes under the name of scientific realism and entity realism. Now, normally those views are distinguished in the philosophical literature, but for my purpose today, I'm just going to cluster them together under the label of unabashed realism. So you can be a realist about science in believing that not only our theories are approximately true, but also the objects that those theories postulates are real. So that's what a scientific realist would say. Or you can be an entity realist. And an entity realist would say that theories come and goes, models come and goes, so we shouldn't really commit to the truth of our theories. But nevertheless, we should be realist about the electron, say, because we can intervene and manipulate on those objects, as we have just done with the cathode rays, okay? I can use a magnetic field and bend the cathode rays, and that's evidence that those objects must be real, okay? There is no spooky action with some kind of phantom here, but there are real objects that I'm intervening and manipulating in a lab. So Ian Hacking, in the early 1980s, defended this view that goes under, you might have come across, his motto was, if you can spray them, they are real. If you can spray electrons, as we've just done, in a way, with cathode rays, they must be real, right? Another kind of position that you find in a kind of decreasing order of strength goes under the name of property realism. Some philosophers have been more selective in the realist commitment. So they think that we shouldn't commit to theories as such or entities. We should commit just to the properties. Property realists would say what is real is not the electron as such, but the properties that, say, the electron exemplified. And there's a great paper by John Norton and Jonathan Bain in the volume that I showed earlier, The History of the Electron, that make a case for why our realist commitment should be confined to properties. And finally, in decreasing order of strength, one can defend some kind of coherent holism and claim that actually, probably we should suspend the realist beliefs as such, because what we have are a coherent, holistic sets of beliefs about those objects without taking the properties of the entities as necessarily real. I say this kind of view exemplified by, for example, this quote by Henri Margenot in his 1950 book on the nature of physical reality, where he says electrons and photons are neither particles nor waves. They are no more one or the other, then they are hot or cold, red or blue. This is not an admission of ignorance. The physicist, in order to grasp reality, has had cause to heed the counsel, thou shalt not make unto thee any graven images. So we shouldn't indulge into making images, representations of those objects, because those objects just defies our classical ways of thinking about those entities. Now, in what follows, I'm not really going to discuss those 3 philosophical views, so I'm happy to answer any question you may have at the Q&A. But I just want to very briefly mention where I stand in this debate. I think coherent holism is the weakest option in a way. I think there's an important difference between rightly claiming that it's difficult to provide the semi-classical images of objects that have a quantum nature, and so therefore we can't really try to portray those objects as one way or another. Another thing is to dismiss any realist commitment about those objects. I think this is kind of throwing the baby with the bathwater, so I wouldn't necessarily subscribe to that kind of view. Unabashed realism wouldn't do either. Now, I apologize because, as I said, I clustered under the label a variety of philosophical views that are quite diverse in their philosophical arguments, and I just don't have the time today to address those philosophical arguments. But briefly, what I think is problematic about what I call unabashed realism is this idea that we can really sweep under a rug the conceptual changes, dramatic scientific revolution, and perspectival images of those objects that scientific communities have produced over time. We have to take that bewildering plurality of images seriously, and we have to come up with an account of how to be realist that take the challenges coming from the history of science very seriously, I think. And that leaves us with property realism. I think it's the most plausible candidate about what kind of realist one should be if we take seriously the perspectival nature of our knowledge. However, I want to tell a cautionary tale about property realism today. In particular, my task ahead is to show that there are historical reasons for being skeptical about a specific brand of property realism, one that takes the metaphysics of natural properties as given, as somehow from a God's eye point of view. And I'm going to take a historical stance, in particular against David Lewis' metaphysical view of natural properties. So if you're not familiar with David Lewis, I mean, it's one of the greatest philosophers of our times. He made lots of contribution to various branches of philosophy. But when it comes to philosophy of science, my field, David Lewis is famous for defending these views about laws of nature, saying that laws of nature somehow supervene on a ontology of properties that are, as he called, the natural sparse properties. So in his view, the right realist commitment is to what he called the mosaics, literally mosaics, of pixel, where each of those pixels is a natural property, the sort of properties that physics tells us. So you can imagine the ontology, the Lewisian ontology, as some sort of Legoland of bricks, where we have fundamental building blocks, fundamental properties, and we can combine those building blocks in different ways to somehow make sense or understand what scientific entities are. So you can think of an electron under this view as some sort of Lego combination of three fundamental natural properties: a certain mass, a certain spin, a certain negative electric charge. As in any Legoland situation, you can swap one block with another, so you can swap negative electric charge with positive electric charge, and instead of the electron, you get a positron. Now, this ontological image of what there is, how to think about electrons, positrons, other entities in nature as a combination of natural properties, somehow resonates with the way in which physicists sometimes talks about those objects. So this is a table taken from a physics textbook, and it's a table that gives you what we think there is in terms of standard models in particle physics. So you have in blue the quarks, here are the leptons in green, and the force carriers are in red. And those fundamental building blocks, fundamental Lego block of what there is, are identified by, well, precisely by physical properties, by electric charge, by mass, by spin, okay? The sort of little number that you see on the side of each of those squares. However, I think there's a problem with this picture. The picture, despite its elegance, is deceptively simple. And the reality, as always, you would expect, is a lot more complex than this metaphysical image might suggest. So in the rest of my talk, I'm really going to leave aside philosophical discussion on this. I'm going to plunge into the history of physics. And I'm going to do it in a very selective way. My purpose is to take a look at a specific episode in the history of the electric charge as a property around 1897, 1906, with the idea of showing you the bewildering pluralities of conceptions that were available at the time about the electric charge. What is electric charge? How do we have to think about it? How can we represent the property of electric charge? My final goal is to show you that despite this plurality of perspectival representation, scientists could nevertheless come to agree, one, that there was an electric charge, and two, about what the electric charge really is. So it's possible to show that perspectivism is compatible with realism. Perspectivism is not a threat to realism, but we should abandon some kind of Hegelian view from nowhere about how to be realist and engage with the actual detail of scientific practice and the history of physics, because we have plenty of reasons for being realist about science from within the history of physics. So moving swiftly to my historical part, okay, I'm gonna put my kind of historical hat on, and then I'll go back to the philosophical part at the very end. What I'm gonna do is just to give you, as I said, a snapshot of about 9 years in this very, very long and complex history of how we came to believe that there are electrons, how we came to believe that electrons have a fundamental property of negative electric charge that you can manipulate, as we've just done with the magnetic field. And this story, in a way, begins with the father of quantum theory. I think is the person that, in a way, set the agenda for how we now think about the electric charge. So we go back to Max Planck, and we go back to the second edition of his theory of heat in 1906, where Planck announced that the measured value for the electric charge E lied in between the values of Perrin and Millikan. And most importantly, what he did was to present the property of electric charge as a fundamental unit, a fundamental physical constant of nature, alongside other physical constants that he himself was introducing at the time, such as the Planck constant and the Boltzmann constant for the law of black body radiation. So it's a wonderful passage from the preface of the second edition of Max Planck that I just want to read out. It says, "Recent advances in physical research have on the whole been favorable to the special theory outlined in this book, I mean, it's quantum theory, in particular to the hypothesis of an elementary quantum of action, is quantum hypothesis. Probably the most direct support for the fundamental idea of the hypothesis of quanta is supplied by the values of the elementary quanta of matter and electricity derived from it. When 12 years ago, I made my first calculation of the value of the elementary electric charge and found it to be 4.69 times 10 to the minus 10 electrostatic units, the value of this quantity deduced by JJ Thomson from his ingenious experiments on the condensation of water vapor on gas ion was quite generally regarded as the most reliable value. This value exceeded the one given by me by 38%. Meanwhile, the experimental method improved in admirable way by the labors of Rutherford, Regner, Perrin, Millikan, Swedenborg, and others have without exception decided in favor of the value deduced from the theory of radiation, which lies between the value of Perrin and Millikan. It's remarkable what he's doing. Planck is setting the agenda for the way we think today about the property of electric charge. A Lewisian natural property was born, in a way. It was identifying the minimal unit of electric charge as a fundamental natural property that he was able to deduce from his theory well before the experiments could be carried out that eventually corroborated the value that he had predicted for this property. And so what is interesting is that further on in the book, in chapter 4, he gives an analysis of various physical constants, so he introduces his Planck constant H. And again, it presents the elementary quantity of electricity, or he says the free charge of a monovalent ion or electron, as having this specific value. And he says that the degree of approximation to which this number represents the corresponding physical constant, that's how he calls it, depends only on the accuracy of the measurement of the two radiation constants A and C. So not only is it possible to deduce from Planck theory the value of E, but E is a physical constant alongside other physical constants that Planck is introducing. So I think in a single stroke, what Planck is doing is to establish a theoretical equivalence between what he called the elementary quantity of electricity and what at the time was still called an ion or an electron. There was some ambiguity in the terminology that represents really the fluidity of opinion that were at the time about that property. We find Lorentz call it an ion. We find Stoney calling an electron. So he decided, okay, my elementary quantity of electricity is the same as what those other people are talking about, okay? Be it Lorentz ion or Stoney electron. He then identifies this elementary quantity of electricity with a physical constant, and then he establishes that the accuracy in the value of the physical constant depend on the measurements of other physical constant. And there is this wonderful passage where he says, okay, if we really want to be serious about metrology, okay, how we establish units of measures in physics, you will notice that there is a difference between some units of measures and others. Some of them depends on the human needs, specific purposes that we may have in scientific inquiries, but others are physical constant. They are independent of us, they are independent of our specific human needs. So there's this wonderful passage where it says, all system of units owe their origin to the coincidence of accidental circumstances, inasmuch as the choice of the units lying at the base of every system has been made, not according to general points of view, which would necessarily retain their importance for all places and all time, but essentially with reference to the special needs of our terrestrial civilization. And he gives as an example the units of length, of time, that were derived from the present dimension and motion of our planet, the units of mass and temperature, that derive from the density and temperature points of water. There's the liquid that is mostly present on the surface of planet Earth. And then it says, in contrast with this, it might be of interest to note that with the aid of the two constants h and k, which appear in the universal law of black body radiation, we have the means of establishing units of length, mass, time, temperature, which are independent of special body of substances, which necessarily retain their significance for all time, for all environment, terrestrial, human, otherwise, and which may therefore be described as natural units. So when I presented David Lewis' image of metaphysics as a very simple, elegant mosaic of natural sparse property, I think that image finds support and corroboration in a way, in a certain ways of thinking about natural units in physics, and we owe that in part, not just only, but in part also to Max Planck and the way he presented, for example, the unit of electric charge in the context. Did he succeed in sweeping away any possible disagreement about the nature of electric charge? Not really, because what was going on at the same time is very interesting. There were other people, in fact, some of people were people that he himself referred to in his book. So one of the scientists referred to is Paul Drude and his work on the theory of optics, who had independent interest from Planck. They were not working on the radiation of black bodies. They were not working on the quantum hypothesis at all. Those people arrived at the same conclusion that there must be an electric charge, but they had very different ideas about what the electric charge was. So I'm going to mention just two examples. So one is, as I mentioned, Paul Drude, that in this 1902 book, so just a year after Planck's original quantum hypothesis, writes that each atom is connected with one ion, again, doesn't call it an electron, whose charge will be denoted by E. Now, E is a universal constant since it represents the electrical charge which is connected with a univalent atom. It's the charge corresponding to valence 1. Now, the reason, I'm not going to read the full quote, you can read it for yourself. The reason why Drude arrived exactly at the same conclusion that E is a minimal unit of electricity is totally different from Planck. His considerations have to do with electrochemistry. What happens if water molecules get electrified, and what happens when we observe the water molecule dissolving into oxygen and water. So if you plug an electric circuit into water, you can observe oxygen on one end and hydrogen on the other end. And there was a long tradition, really throughout the 19th century, of people that were trying to understand the phenomenon of electrolysis. So some of the very first models go back to the German chemist Theodor von Grotthus, who in 1806 came up with a model of the electrolysis of water. You can really see my pointer, Sarah. Yeah, so some of the pointer doesn't seem to be working, but Anyway, he had this model, the one you see on top, where he believed that in the presence of electricity, water molecule get electrified. So you would have the hydrogen with positive charge and the oxygen with negative charge, and they form like a chain, and they kind of hold hands, so that you can see at some point the oxygen coming out on one end and the hydrogen on the other end. Through these kind of experiments on electrolysis, people came to the conclusion that there must have been a minimal unit corresponding to chemical valence 1. And this is the reasoning behind the Helmholtz and behind Drude conclusion about the existence of a natural property of electric charge. And if we switch from electrochemistry to, going back to JJ Thomson on cathode rays, the story gets even more fascinating. So 1906, JJ Thomson gets a Nobel Prize for discovering exactly what Marcello showed, namely that there are carriers of negative electricity at work in cathode rays. But in his Nobel Prize speech, he doesn't talk about the electron as such. It doesn't use the term electron. And even more interesting, if you read the speech given by Claesson, the president of the Royal Swedish Academy of Sciences, it's even more interesting. You find it online. He says, well, JJ Thomson was following in the footsteps of Maxwell and Faraday, especially Faraday, 1838 discovery of the law of electrolysis. And this is what Claesson says. He says, even if Thomson hasn't actually beheld the atoms, he has nevertheless achieved work commensurable therewith by having directly observed the quantity of electricity carried by each atom. These small particles are called electrons, have been made the object of very thoroughgoing researches on the part of a large number of investigators, foremost of whom Leonard, last year Nobel Prize winner in physics, and JJ Thomson. So you can find the Nobel Prize speech online there. So it's interesting that he's given the Nobel Prize, but with a sort of caveat, like he didn't beheld the electron, he didn't really call them electron either, but nevertheless, he was able to perform experiments that were able to measure with precision the value of the charge to mass ratio of the object that we now call electrons. And so what did he believe? What did JJ Thomson believe about those objects? Well, this is where the perspectival nature of our knowledge comes in again. He wasn't endorsing Planck quantum hypothesis. There is no mention of quanta in his work. And he was working within a tradition that, although related to the studies of electrolysis, was also at a distance from it. He was working within a perspective that might be called the Faraday-Maxwell perspective. So it's a tradition that really begins with studies of electromagnetism, Ørsted in Denmark, and then Michael Faraday at the Royal Institution in London, who back in the 1820s found out the existence of magnetic lines of force. So those are Faraday's original drawing of what happens if you have ion filings and how they form patterns, like circular patterns around the magnetic field. And in the 1860s, you still find Maxwell in Edinburgh, where I am, coming out with models of the ether to explain phenomena of electromagnetic induction. So people knew that there was a connection between electricity and magnetism. Faraday discovered that if you move a magnet inside the metal ring, you can induce electricity in the wire. But how is that possible? How can electricity be produced by a change in magnetic lines of force? James Clerk Maxwell in 1861 was working with mechanical models of the ether. So this is a famous honeycomb model of the ether, where he thought, okay, imagine there is this thing called the ether that pervades all space, is elastic, is invisible. Imagine that this ether forms hexagons or cylinders. And the cylinders move, and by moving faster and faster, they generate a magnetic field. And imagine that there are idle wheels among those cylinders. So the cylinders move, and the idle wheel move. That's how magnetism induces electricity in the wire. So it's a very ingenious mechanical model of the ether that obviously was false, but helped Maxwell to arrive at this discovery that actually there is an electromagnetic field, and the light itself is nothing but an electromagnetic wave. He was able to arrive at that conclusion 12 years later, precisely through models of the ether like this one. So we find that about 30 years later, JJ Thomson in Cambridge at the Cavendish Lab is still working within this Faraday-Maxwell tradition. His concerns are not about the electrolysis of water, are not about quantum theory, they are about electromagnetisms. So it's still in 1903, so just 3 years before his Nobel Prize, he gives this series of lectures at Yale called the Silliman Lecture, that again you can look online, and he talks about Faraday tubes as tubes of electrostatic induction, and he believes that electric charge is just positive and negative charges at the two ends of a Faraday tube, and he believes that you can stretch and bend an elastic Faraday tube, and eventually when the Faraday tube gets broken, electricity gets displaced. So these are from the Silliman lecture. He talks about the natural unit or atom of electricity, but the way he arrives at the idea of a natural unit has nothing to do with physical constant like Planck. It has to do with his experiments with electron gas and cathode rays, and there is no whatsoever mention of the quantum hypothesis and the explanation of the Röntgen effect. I'm going to close here this kind of a snapshot on, as I said, those 9 years of the history of physics between 1897 and 1906, because I want to quickly go back to my philosophical topics and try to draw very quickly some take-home messages. So my first take-home message from today, going back to the issue about realism and perspectivism in science, is that property realism, in particular, some sort of Lewisian view of natural property, is somehow too simple to capture the complex nuances of these stories, because it assumes a metaphysics of natural properties as given to us, as some sort of God's eye view on what there is. We never have such a God's eye view on what there is. The reality is that we come to discover what there is through an engagement with experimental practices that are every inch of the way perspectival. So my second message is that really our knowledge of the electron and of the electric charge is perspectival. That's where perspectivity comes in at least 3 ways. It's knowledge produced by experimental tool measurement techniques that are rooted in well-defined scientific perspectives. So I've given you 3 examples of those scientific perspectives at the turn of the century. The Max Planck quantum perspective, the Helmholtz-Drude electrochemical perspective, and the Faraday-Maxwell perspective of JJ Thomson. And it's also knowledge tied to the scientific theory, obviously, that were linked to those instruments. So as I said, JJ Thomson was not working on the quantum theory, and Planck was not working on electrolysis. And it's knowledge that reflects wider social practices of given epistemic community. I think it comes as no surprise that JJ Thomson at the Cavendish Lab in Cambridge was working within the Maxwell-Faraday tradition that was so popular in Britain at the time, in the Victorian Cambridge, where theories of the ether had a much wider application well outside physics. So there was all this literature about spiritualism and that somehow ether theory feed into. My third and final take-home message is that the history of the electron and the electric charge is a history of success from within. We should be realists about science, and we should believe that science tells us a true story about what there is. But not because we have an Hegelian view from nowhere, but because if we look at the history of science, if we look at the scientific practice, we have plenty of reason for understanding how scientists working within different scientific traditions, with different experiments, different tools, different contexts, that came to agree about what there is. And so this perspectival consideration don't make the electric charge any less real as a property than you would have in other accounts. This is just to show that the electric charge is not a Lewisian natural property, that the world doesn't come prepackaged with such sparse natural property, waiting for someone to stumble on them. In a way, it's our success, it's the success of our experimental practices, our ability to come to agree on what there is, despite the perspectival nature of our knowledge. And this is because scientists across different perspectives typically share a commitment to get things right. They share a commitment to abide by the evidence, by scientific standards. So this story shows us the importance of accuracy in measurements. So you've seen Max Planck, how he insisted on the value for the electric charge, the original discrepancy between his value and the value found at JJ Thomson, the importance of having refined value for the electric charge, or explanation within the constraints of laws of nature, the role the Faraday law about electrolysis played in this story. So I think this gives us plenty of reason for being realist about science, while also taking on board the view that we don't have any Hegelian view from nowhere. Our knowledge is situated, is historical, and nevertheless is our safest bet to what there is. And this is the grant that goes on until 2020. And if you're interested, you can go to the website and you find some more articles and links to similar publications here. Thank you very much.
Questions from the audience?
I actually have 2 questions. So, did the Millikan oil drop experiment in this country, I guess, did it have any bearing on electric charge, or actually charge the mass?
Yes, it definitely did. So we've seen in the quote from Planck that he mentions how the experiment on Millikan and Perrin, in a way, provided the kind of the 2 boundaries for fixing the range of plausible, likely to be true value for the electric charge. So I haven't talked about Millikan or Perrin in this particular paper, but yes, it played an important role precisely in refining the accuracy of the measurements that increased the confidence in the existence of the property.
So my other one is, of course, this notion of charge as being a real property is we come to it through different experiments. It's a very interesting point. But our knowledge changes over time or evolves. So, I mean, we now know that the charge, quote, depends on how close we get to the electron. Through particle physics experiment, as you collide these define higher energies, you can actually see it affecting larger and larger charge. So how does that kind of theoretic description enter into the evolving story and light to these various different philosophical points of views about reality?
That's a very good question. So one of my main concerns in the project is precisely to rethink some traditional philosophical notions, like notions of natural kinds, when we take perspectival considerations into account. So the example that you're mentioning is very pertinent because the question is not just what happened in that particular point of time. This is an ongoing process. Our knowledge is perspectival all along. And the question is, how can we retain those realist commitment in the face of ongoing and evolving images of those objects all the time? So the intuition that there I have is that we should really think of our realist commitment as some sort of proceedings in the garden of forking path, where at each juncture, as more evidence becomes available, we can make inferences about refined value of the property or about possible new properties that we didn't know before. So it's a knowledge that is constantly evolving with us, but in a way there is something that stays the same. Now, this is why in a way I thought at the beginning the property realism is the most plausible of those 3 philosophical views, because we have these intuitions that there's a cluster of, however you want to call it, property that somehow stays stable across time. The problem is that those properties are not given once and for all. Our images of the electric charge change all the time. But I think it's possible to retain a realist commitment precisely because if we think of shared standards that epistemic communities might have, so even if they work within different interests and experimental tool, a similar commitment to accuracy in the measurement, for example, is really, really important, because no matter how false the belief of JJ Thomson might have been about the Faraday tubes, he got right at the charge to mass ratio, and that's the reason why we still remember JJ Thomson for his experiment on cathode rays. So I think it's that common kind of shared commitment to standards, like accuracy measurements is just one of them, but there are many of others that one can mention that I think is what holds us together as a community across the history of science.
So I was interested in a similar point to the one that Miles just made. It's interesting that you say that our knowledge of charge as a real property comes from this convergence of perspectives, and that's telling. But I'm not sure which way it tells. I mean, you may tell a story that goes something like this: that perspectivalism is kind of a barrier to realism, and what we're getting here is like, well, these different perspectives are giving us the same number. So there must be something sort of perspective independent that we're getting at here. Right? So I'm not sure what the lesson of the convergence is supposed to be. Because one way you might take the lesson of the convergence is this is how we get outside of all perspectives, because they agree. So the perspectives could be all wrong, but we're agreeing on something.
Okay, that's a very good point. So when I said just in the previous slides that Howard is a story of success from within, right? That's where I think I kind of differ from the standard realist story that says, okay, there is this mosaics of property, and we just, it's just a matter of how you approach it from different angles, but at some point you'll stumble into it. I think we never really can claim to have that sort of God's eye view that tells us, and now we got it, and we got it right, because as we just have heard, I mean, if you switch to 20 years later or 50 years later, our images of those objects keep on evolving. And so the question is, okay, how does different images and perspectival representation latch on to what there is? So I like to think of progress in science and success in getting things right as a kind of an internal process, as opposed to, and now we're stumbled into its mosaics of metaphysically given properties, because I genuinely think in no specific point or juncture in our history of science we can ever claim that now we have got it right, because who knows, maybe in 200 years down the line we may have big scientific revolutions about, I don't know, the electric charge. But we have perfectly good reasons for explaining why we have the realist commitment at any particular point. There are reasons, there are warranted inferences that we make, and there is evidence that we use to make those inferences. So the fact that those different perspectives somehow overlapped, to me, is not driven by some a priori metaphysical property that said, here I'm the linchpin on which all those perspectives somehow converge, but it's really driven by the perspectival engagement of those scientists in different ways. We're really making inferences. So if you read Thomson, he says, well, we've got a problem here. The problem is that if you read Helmholtz and people working on electrochemistry, they've come out with a charge-to-mass ratio that differs from the charge-to-mass ratio that I found in my experiment. And there are two ways of going about this. Either the charge of the monovalent ion is different in the cathode rays and in the electrochemistry case, or the mass is different. And so it's via that sort of elimination process that arrives at the conclusion, well, it has to be the mass that explains why there is some disagreement, and the mass of the electron is much, much smaller than the mass of the hydrogen atom. So that's how he arrives at the identification of the first subatomic particle by a process of inferences and kind of elimination, looking at evidence that was discrepant. But yes, I don't know what you see, but I agree with the question of, okay, what comes first? Is the metaphysics that drives the convergence, or is some sort of internalist story that one can tell of how we come to agree about what there is, even if we don't have any privileged access to it? Yes, I think there's Adina.
So I think this might be along the same lines, but I was kind of puzzled why, or what the basis was for discarding the Lewisian theories so quickly. So it seems to me that his theory is a metaphysical theory about the nature of laws, and not an epistemic theory about whether or not we have access to the properties. So maybe you can explain.
Sure.
What the reasoning is.
Yeah, no, I apologize, because as I said, there's this philosophy at the beginning, at the end, and there is this long historical episode in between. So there is a longer story. There's a story I haven't really told today about, obviously, Lewis' view about laws of nature, which is related to his view about the metaphysics of natural property. But in a way, his view about laws of nature, which I've written elsewhere, is less relevant to the kind of story I wanted to tell today. One thing that I always found it very interesting about Lewis is that he has a very simple, minimalist ontological commitment about what there is. And it's a commitment to this, as he calls it, a Humean mosaic of sparse natural properties. So in his view, the ontology of nature reduces to a simple mosaic that is Humean, because it doesn't believe there is any glue, there is no causal connection, they kind of holds all those pixels together. But there are those pixels nonetheless, and those pixels are pixels made of natural sparse properties that together can provide spatiotemporally localized matters of fact on which he believes laws of nature supervene. So that's his idea of the Humean supervenience. Much as I like the simplicity and the elegance of his metaphysical picture, one thing that I always found problematic, but maybe it's because really I'm a kind of a history and philosophy of science person, is that that picture is given to us. We are not given any other metaphysical or epistemological reason for doubting that there is such a Humean mosaics of properties. So the assumption is we have a view from nowhere, and if we could have such a view from nowhere, if we could uncover the veil of Maya, that's what we would see. We would see a basic ontology, a basic metaphysics of natural properties. And that's what I have, I think, problems with. The problem is we never really open the veil of Maya to look at what's underneath. What we do is to engage with the instruments, measurement theories, cultural practices that every epistemic community in the history has produced over time. And nevertheless, we're pretty good at making, good inferences, good guesses about what there is. So I may well end up agreeing in the end with the final kind of outcome about what there is. But the question is, how do we get to the outcome? Is that because we have any neutral standpoint from which we can ever have that access? So Ned Hall has this, I think, beautiful metaphor. He calls it the LOP, the limited oracular perfect physicist. So he says, if we were a LOP in David Lewis' sense, so if I were a limited oracular perfect physicist, I could look behind the veil and see, oh, here's mass, here's charge, here's the spin, or whatever other fundamental properties there are. But we are not oracular perfect physicists. We are just human beings that use the instruments and the theories and the techniques that we do have. And so that's where I think I kind of I see problems with the metaphysical picture. So my problem is not so much with the properties itself, although I have questions about, okay, to what extent those properties are given once and for all, to what extent they change over time or they evolve. But it's about our epistemic access to metaphysical claims about what there is.
Yeah, I would like to reinforce that, because if you go out and you ask physicists, what's an electron? Even the physicists here in this room, if you ask, okay, what's an electron? I bet you they're going to get very different answers.
Right.
Because if you know any quantum field theory, you're going to say there is no electron. They're just fluctuations of fundamental quantum electric field.
That's right.
And so to say what an electron is, I think, is a very dangerous game to play. Because what an electron is, as you said, depends very much on the context in which where we are in the history of science and the kinds of measurements we can make about an electron. But there are some things, I think that's what Peter was saying, there are some things that we can converge on. For example, the conservation laws that must be associated with particle interactions where an electron takes place, right? You say the amount of electric charge before and after the collision is going to be the same. So that means that there is something there that is carrying that property, electric charge, which is measurable, and it works as a kind of like a signpost for particle physicists in general. So I wonder if you mentioned something about community, and I wanted to ask you about this. So is it really about consensus at a given time? Because clearly, these different perspectives were kind of floating around, and eventually they converged into there's this particle of negative fundamental electric charge and spin a half, and mass, whatever it is. Let's call that an electron, put it in our little manual of particle physics, properties of these things. is that how it works? Is it the definition of what an electron is something that we look at consensus, and then eventually, as our perspective changes, you know, the consensus may change with it.
Okay, thank you for that, and thank you for making me realize I need to be very careful on this, because I don't want to suggest that it's a matter of consensus. This is a realist view, okay? It's not just intersubjective agreement. So
it's not subjective, right? Because it's really based on measurements, physical measurements of the properties of the given.
That's right. So, and that's important, right? I mean, experimental evidence is there, is the, if you like, is the tether of our perspective, our representation. We have to respond to the empirical evidence all the time. So it's not a matter of coherent holism. You know, there's a community that coherently holds a set of belief about that object, but then equally you can discard the sets of belief, have new sets of belief in place. So I want to resist, in a way, the a picture of a Lewisian Loppian access to metaphysical property, as much as I want to resist the opposite temptation of kind of going Kuhnian, entirely Kuhnian, Thomas Kuhn on this story, because that would be the obvious natural temptation. Kuhn made this very, very influential claim that because our science is full of scientific revolutions and conceptual changes, there cannot be truth and there cannot be natural kinds as such. What we have are scientific paradigms, and within each paradigms, different communities at different historical times may hold dear to some beliefs about, I don't know, phlogiston or caloric or ether or the electron or whatever have you. I want to resist that view because that's, I think the risk with the view is just the opposite with the risk of the Nagelian view from nowhere. You end up with a discontinuous fragmented image of how science works all the time, where a community gets replaced by another community. There's a coherent system of beliefs, but could be a different system of belief in place. And the whole purpose of the project is to show that we can endorse, I think, the good of the Kuhnian picture, which is really this idea our story is historical and culturally situated. You know, we don't have a oracular access to what that is. But that doesn't necessarily land us into some kind of constructivism or into some form of it's just consensus of different communities that may come to agree about something. Ultimately, we respond to evidence and we make informed, rational decisions about what we believe to the best of our knowledge there is. And we do that all the time. So I want to defend a kind of inferentialist view about what there is. In a way, a view that, well, lots of people may chime with the view of people like Putnam or Sellers or, you know, Brandom, but the idea that really it's our giving and asking for reason and the way we respond to evidence that provides an important anchor to our beliefs.
But there is no finality to it.
No, there is no final, as I said, mosaics of natural property. We're gonna, ta-da! Yeah.
Because, you know, right now we say an electron is a point particle, which in a sense really doesn't make a lot of sense. Like, what does it mean for something to exist and be a point particle, right?
Yeah.
But it could be that if you build the large linear collider and 20 years from now, they will find out that, hey, the electron is actually a composite particle. It's made of two particles and a fifth force that we didn't even know existed. And then, boom, we have a completely new way of thinking about the electron, which is kind of something that happens, you know?
Yeah.
Even though it maintains the properties of magnitude charge, it
Still does that.
Yeah, like that. Yeah.
Yes, Selena.
I guess I buy everything that's been said, but I still, I don't see why that's not consistent with a Lewisian view. That, you know, well, we thought there were Faraday tubes. That was a property that you know, seemed to explain the data at the time. And now our new explanation latches onto other properties. But like, to the extent that we get it right, we're getting at the true natural kind properties that there are. So it's a fallibilist.
It is, yeah.
But it's still.
It is a fallibilist view. I don't know what Lewis would say about, I think, you know, not that I have anything particularly against Lewis. What I see missing in Lewis is any engagement with precisely those kind of consideration. I'm not aware of him addressing questions about conceptual change or plurality of images for those objects. I don't know what he would have said about that if he had engaged with it. It could well be that it might have been quite sympathetic to the view that these metaphysically given natural properties are compatible with plurality of perspectival representation. It's just in a way, it's the fact that it doesn't discuss those sort of concern, which I take it really from the history of science, that makes me worry about the, as I said, deceptively simple image of, okay, here's the metaphysics of nature, and now build your system of laws of nature on it. I don't think we have such an access to the metaphysics of nature, but we do, but it's a very long and complex story that involves lots of detours and, full step and dead alleys and whatnot.
Any more comments or questions from the audience? All right, thank you so much, Michela.
Thank you very much for your questions. Thanks.